everybody knew. We started with Jianxin, and then we ended with Jianxin. Xin means you, I guess. So we start you and
It's the same character.
Yeah.
Same character.
Yeah, it's same character.
Same character.
Jianxin is a creator you, and Jianxin is a prisoner you.
Always new.
All is new. So we don't have to talk about all this stuff. So we don't talk about this stuff. All right. So last of today will be Jianxin Root from USTC. Yeah. Detecting the OpenStreet.
Thanks,
How about your
Oh, I'm the putting here.
Oh, okay.
Yeah, I'm good for next time. Well, thanks to the local organizer for their effort in organizing this workshop, and also for giving me the opportunity to be the last speaker of the workshop. Well, back to my talk. Yeah. Here's the title of my talk. Yeah, it's basically the update and the continuation of the talk I give in the last workshop in NTHU regarding the open-spin pair production in type 2 spin theory and its possibility of detection. The primary purpose of this effort is to seek some unique spin signature which can be used to test the spin theory without the need of quantification from NT4. The talk is basically based on a few of risk works, some of which are collaborated with my students, Jianxin, Wu, and Wu. So I guess that after listening almost all this talk, everybody gets tired. Yes. So I try to keep the talk as intuitive and keep the technique part as this as possible. Yeah. Well, the outline of talk is this. So let's begin. Yeah. We know now an isolated E-brain in type 2 spin theory cannot give rise as a so-called open-spin pair production when the volume electrical flux applied. The simplest setup for creating the open-spin pair production is to consider a system of 2 DP brain, which places the parallel separation with each carrying a different electrical flux. Probably for the simplest case, we just let it continue. For example, if you take the electric flux on this brain is larger than this one, yeah, once a virtual pair of open spin created due to quantum fluctuation, for example, yeah, for the electrical force acting on, for example, this end will be larger than this end, so this virtual open spin will pull towards the inside of the spring. But the same token, this one will put outside. So certainly we have certain probability to create the pair production without even doing any calculation. But for practical, for realistic electrical field you apply, if you calculate the pair production rate, you find the rate is vanishingly small. So in that sense, we don't have any practical use. Yes, if we wanted to for the purpose of this of the effort, yeah, we need to find a way to enhance this pair production. So the rate can actually be enhanced if you apply a magnetic flux in this way. Yeah, basically for example, the electric flux is pointing to one direction, the magnetic flux has to be to three directions, has to be this way. That's the most efficient way to enhance the pair production. Yeah, the reason is pretty simple. So we know the larger electric flux of the difference between the electric flux difference between the two brains. So we expect the larger the pair rate to create. The use of the adding magnetic flux is just for the purpose of reducing certain modes of open spin mass, which we are going to discuss later on. Yeah. So that's the reason why adding magnetic flux can enhance the pair production rate. Yeah, here we use just a dimensionless one. Yeah, the usual flux is defined this way. So then we can calculate the pair production rate for the system we just did with this just flux I described. So if you're interested in the technical part, just the paper I quoted at the beginning, or we calculate this one. So actually, I discussed this. I give the risk from in the last workshop here. Yeah. Okay, the rate is given as. So here we just the y is the distance between the two EP branes, and in addition we choose the two parameters, nu 0 and nu 0 prime. The nu 0 we call it the electrical parameter, which here is related to the electrical flux on the two EP branes. Yeah, if the only thing I want to point out, if you increase any flux, you increase the electric parameter. Yeah, the magnetic parameter is related to the magnetic flux on the two branes. So in general, for if the laboratory condition, these parameters are electric flux are small compared to spin scale. We know that. Yeah, we're going to discuss that mention it later on. So if nu 0 is very small, yeah, the magnetic normally is also small. So this guy, okay, let me point out. Okay. This factor basically counts all the opposite excitation contribution to this rate. So if you for the very small nu 0, much for example almost 0, and nu 0 almost 0. So basically you see this factor almost gone. So basically this guy is 1. So what I'm saying here is for the very small nu 0 much less than 1, nu 0 prime, this is almost 1. So basically we ignore all the highest excitation modes of the opposite but leave the lowest mass most. So if you do this, you will find the rate can be approached by this. Basically we said that, yeah, basically we said this is 1. Yeah, as one thing I need to point out, within this magnetic flux, the P has to be greater than 3. Okay, with this, you will see, just if you count the dimensionless pair production rate, so the only parameter, the only place we will see that depends on the dimensionality of the range is this one. Since the P greater than 3 and nu 0 is much less than 1, so the largest range we would expect is for P 3, which just is 3. Yeah, maybe probably we can take it as the water value. For example, if you take a PP4, the raised ratio is given by this factor. So it's small. It's actually since nu 0 is very small, so this guy it should be very small, which will be given numerical as demonstration how small it is. Yeah, any more magnetic flux, for example, PP5, you would expect it at one more electric flux. Normally, yeah, if you add that, you will not enhance the rate but actually reduce the rate. So for now, for the simplicity, since we are only can control the brane we are living, so we just set the other brane flux as 0. So let me give an estimation how small the factor I just mentioned is. For example, the spin scale is something like at least a few TeV to this. So for example, the current level for electric field is the directed electric field something like 8 ME squared. ME is the mass of electron. If you put in the TeV something like this, so if you plug in this for the F1 because we said the other the flux on the other one is 0, you estimate something like 10 to minus 21. So the nu 0 is you estimate etc. So this factor is 10 to minus 10. In other words, yeah, the only chance if we want to see the detector rate, the only chance probably is for this brane. Or the other brane, at least the rate is smaller by 10 to the power 10 to 11, 10 to minus 11. So for now, we just for the following year, I only focus for these 3 brane. Okay, so in terms of lab electric and magnetic field, we can write the dimensionless electric flux and magnetic flux using the lab electric and magnetic field. the rate I given before of this one, if you take a P3, can be expressed simply as this one. But here we take a mass, we introduce a mass scale, which is given by the tangent times the spin length of the spin length. So that's basically the lowest mass of the open spin. Like this. So if you look at on this, it looks like it has nothing to do with spin shift. Yeah. Now we try to explain what are those modes contributing to this field production rate. For this, we just first we turn off the electromagnetic field. So we now consider this optically connected two discrete branes. Yeah, the spectrum is given by so the lowest one because of just the spin length times the extension plus the number operator here. The Riemann sector gives us the fermions, and the Navier-Stokes sector gives us the bosons. So like this. So the Riemann sector gives fermion with just the number operator greater than 0, or the Navier-Stokes sector gives the boson like this. So since the electric field we apply is very small, so probably the things we will first just focus on the ground state for the GSO projected state. Yeah. So if we put the two D3 brane, for example, each on top of each other, it should give the total number of degree, the massless one should give 4 times of this, right? So that's actually give from the 4 D3 brane point of view, just give the 4 D equal 4 into superMS. So if we move the two D3 brane away from each other, so among these the 4 generators, 2 of them are broken, become massive. Always the same mass, because we know when we the D2, 3 brane put on top of each other and separate, the supersymmetries keeps the same. That's why all the modes should have the same mass. Yeah. This is just from the field theory point, just reflect the spontaneous symmetry break from Y to 0 to non-zero. The 2 broken generators actually give the 16 pairs of charge and charge degree freedom with respect to the brane of the. We know that if we leave on the brane, we can only see the 2 ends of the open spin. Just appear as massive charge particles. So this basically explains what we have why this factor is 1. Now we could try to compare the rate we calculate with the QED rate. For example, the QED scalar is given by this when both electrical magnetic field are present, and the QED spinner, and for W boson. So we see how this connection between what we calculate with the 3 guys. For this, we let me take the magnetic field that comes off the magnetic field. You will find the rate we calculate, set all the mass to be same. Because for our case, all the 8 fermion and the boson, the 16 pair of the charge particles all have the same mass. So to do comparison, we set all the mass to be equal. So the first thing you find is the rate we calculate is equal to 16 times the QED scale if we identify the scale of mass, the same as the mass we have for our degree. And equal 8 times W QED spinner and the 16 of 3 W boson of B5. So this one actually easy to understand because of the QED just count 1 pair of degree freedom. And then for spinner we count 2, because spin up, spin down with 2 degree freedoms. That's why here. For W boson we have 3 degree freedoms. So that's why we can give this. Yeah. And now we consider the other limit for large B over E. The same thing as we said B non-zero and E almost is also given. So you will find that you see the rate will become like this. So you see the rate we have here, same thing like W boson, like vector field, massive vector field. There's a reason for that I'll really explain. And the other is that except all the exponential part are different, the prefix are all the same. So that implies for the scalar we only count one pair of degree freedom of charge and charge. So that implies we have for all the others the contribution to the degree freedom contribute to the rate should also be same as the scale. Yeah, we're going to explain in a second. So for explain what do we have? We just consider a massive charged particle with spin as in a weak electric field. So the energy spectrum is given by this. So this basically is Landau motion, and this just deals with the charge particle has magnetic moment coupled with the magnetic field, and this is the original mass when we turn the B off. So we will find, for example, for spin zero, this one we don't have this. So only for the lowest Landau level, we have contribution only for the electron. That means that if you turn an electromagnetic field, its rest energy will be lifted up with E equal D. So that's why we have only 1 degree freedom for scalar. That's all we have. For spin for the spin half particle, so if the spin polarization is point the same as magnetic field, and we take positive charge part, yeah, then you see this guy just cancels this guy since we take the lowest one there. So that leaves the mass unchanged. But for the other polarization, we add up, right? We should add up twice. That means at least tell us the mass when the magnetic field, the spin points the same magnetic direction, the mass lowest mass will not change. But for spin one charged spin one particle, if you come to the polarization, the spin point the same as the magnetic field, because we have here is 2, here's 1, so we give negative 1. So that means that if you apply magnetic field, we can lower the mass effectively. Yeah. But we have the other two polarization, for example, as B dot S equal to 0 and B dot S equal to -1. So even though for vector field with 3 polarization, the lowest one is only by we have only the mass is lowered by only by the polarization between the spin point the same as magnetic field. So here we have if you come to the lowest mass, just given by this. So if you use this one, then you can easily explain this formula. Yeah, this basically just at least for 3 of this one. Yeah, basically just should be summarized. You can give just by this formula. So the reason we have only count 1 pair of polarization because we can count this just lowest mass one. For all the other mass, because this one is for 0 electric field and the finite magnetic field, even though it's small. So that the B of E is something like infinitely large. So that means any other, for example, even though for the vector field massive factor, even though we have 3 polarization, all the other mass splitting higher than this one compared to this one basically vanishes if you do the radical calculation. So this basically explains both this and this behavior. Okay, now we just go to a little bit further. Since we know the 2 broken gate generators each give the actually 40 into 4 massive super-units, which actually have the 5 massive scalars, 4 massive fermions, and 1 massive vectors, but the charge of opposite under the U1. So given this, we should expect the following formula. Since even though we do this, we are using spin computation. We know for the weak electromagnetic field, we only count those super-units multiplied. Yeah, the charge is super-units, massive super-units. So we have the 5 actually scalar. But here we have said that all the mass is be the same as we have here. So we should expect this. Yeah, if you plug in the formula, you check that. Yeah, you just using this formula, and all 3 set all the mass to be equal, you find that this is indeed true. So Even though you expect this, but the two calculate completely different. We do find that that's the reason I say, even though well, this is a check what we, the rate calculator should be right. Yeah. So this also, this one will also give you experience, yeah. So in addition to what I said earlier, you also can check this. Okay, given what I said, yeah, now we move a little bit further. Yeah, we now consider the small electric field applied, but the magnetic flux can be large. Yeah. Now for this case, yeah, you just, because I said earlier, for the spin half, yeah, because we have the 8 fermion and the 8 boson pairs of the charge mass modes. So for the Riemann part, we don't care because the lowest mass keeps the same as before. Now we focus on the intersect for the bosons. So the boson, if you have this, you find the energy spectrum is given by this original mass. Yeah, adding a magnetic flux, finite magnetic flux is given by this. Yeah, if you again we talk lowest lambda level, you will give the mass. Sorry. Yeah, you put the mass here is given by this, so the energy spectrum. So this is spin operating. Sorry, this is spin operating. Yeah. Then you find that if you consider actually the lowest energy is given by this GSO projected state. If you act in that mass operator on this state, you give the mass lowest mass spectrum is given by this. So we have this kind of shift. Normally we call the spin calculator, we call this tachyonic shift. Yeah. So if you take the weak magnetic field, it doesn't give you what we have before. Yeah. Okay, now we come to discuss this rate. Can we have a possibility to detect this kind of rate produced? Yeah. Since I said earlier, even the supersymmetry actually is broken by the applied flux. Before you turn on the flux, the supersymmetry, one of the two distribute on top of each other, and you separate the supersymmetry both of them to become a supersymmetry. So in general, you should expect this mass scale should be at least larger than larger than TeV, because so far we don't find the supersymmetry. So in that case, so in order to detect the electric field, for example, if the POV is on of the 1. So in that case, in order to detect the pair production, the charge times the electric should be on order of this m squared. Now this actually is easy to understand that. Yeah, from the Breen observer point of view, just like Schumann pair production, you have the virtual electric charge, a positive electric and magnetic one. So if you apply electric field, the uniform, then to separate it, you want to see that experimentally, you have to separate. So the way to do that, you have the force acting on this virtual pair is given sort of by because each of gives like this, right? So if you times the distance, that means the force times the distance. This is just the constant natural units, just m. So this should give rise to energy conservation. From virtual one, you want to put the real one, you need to give the twice of the mass, right? Yeah, this just rest energy. So given this, you will find that this one just something like m squared. Yeah. So this basically is but if the POV is much greater than 1, they will come a factor here. This gives you like this. So this gives you something like the electric mass, which is the m squared minus EP. Yeah. So because for this case, the P is large, E is small. So the only other case you have to have the magnetic order of the m squared, such that you can have even have the small electric field. You can find the pair production. But the issue is that since the m is order of the TeV, but the counter lab limit is something like this, 10 to the as electron mass is much smaller than this. So long the system we choose like what we choose here, it seems impossible to find the pair production because the lab electric field magnetic are too small compared to the SUSI scale because we don't break SUSI before we turn on the flux. So it's hopeless. So now we have to find a way to overcome this. That means we have to break SUSI before we turn on the electromagnetic flux. So for potential detection, we need to have a non-simple symmetrical system of deep brain, even in the absence of the volume flux. Yeah. Then we have the corresponding mass scale is comparable to the current lab electric field. Yeah, because of this. Yeah. So actually, we just consider system one such as it actually exists is the signal D3 and D1. Yeah. This guy has no system from the beginning, and the D1 appears effectively as a spin scale magnetic field such that it can give the small mass spin effective mass scale. But this one, I guess probably most of us know, yeah. A D brane, DP brane, if a carry constant magnetic flux is equivalent to a D minus codimension 2 D brane, which actually delocalized along the magnetic direction. So in our computer, the D1 just to the D3 just something like a spin scale magnetic flux. So if you do the rate computation by the yeah, you find this one. So here we just on D3 we have this kind of electromagnetic just left. We take it as our laboratory one, yeah, which should much less than 1. Magnetic flux is given this, but on D1 we don't add anything. Yeah. So the mass here is still as same as before, but the magnetic parameter new 0 prime is given by this. Since the G is much less than 1, we can set it equal to 0. If it's 0, it's a new prime, just precisely half. But for a small one, this one should be around the half. So now we come to discuss. So among the 16 plus 16 modes, impedance rate, the loss energy modes are the charge and anti-charge, actually also the vector mode. With the effective mass is given by this. So only for this charge in the pair, we have a possibility for detection. So concretely, if we said, for example, if this one is also sort of the spin scale, and this one, if on the spin scale, two can cancel equal small. So if, for example, if you said that this mass scale is around this, that means we said that Brins repulse has a few times of spin scale. So then this give an effective mass. Then the electric field can be as small as you, depending on how you can tune the house, the Brins is. So for this case, we don't have the issue. So that means we have the possibility. So yeah, the good thing, the reason we want to tune on small magnetic flux is we want to, if we experimentally, if we want to check this rate, we have to check against the applied electric flux as well as applied magnetic flux. We see how the, for example, if you detect the current on the brain created by pair production, how that will depend on the electric flux and magnetic flux in the line. That's the first. So that's basically is my story I want to tell you. So I just tell you what is implied. If such a detection, for example, as an electric current due to the pair production, is indeed possible, it first implies the existence of active dimension. Because of this, the open string pair is connected to the D3 brand D1 string, which is to the brain observer is along the transpose direction. So if you detect the signal, it must be from there. We have the other choice. If the pair plate, the four end on the same brain, we know that cannot produce pair production. So this tells that. The second thing, it gives a new way to verify the underlying spin theory without being to compare between informed, so long as the pair production is concerned. Yeah, that's basically the implication. Yeah. So that's basically what I'm trying to tell you. Thank you. Yeah.
So implication?
Yeah. At the beginning, you mentioned that the reduction rate is highest in 1p equal to 3.
Equal to 3. Yeah, that's for the two brain are both have the same dimensionality. But that one, since we don't break SUSI,
I just wonder, what is there intuitive way to answer why it's 3?
Oh, why is it 3? Okay, back. That's probably. Yeah. When you calculate the rate, yeah, you get. Yeah. The only thing depends on the dimensionality of this factor. The new zero practical user is much better than 1. So the peak of 3 should give the largest one.
Where is 3 from? Because
where is the 3 from? Good. Yeah, here it is. I say the most efficient to give the pair production is this kind of flux. So here is the electric has to be at least point in one direction, right? The magnetic has to be 1, 2, 3. The reason for that, let me I give you a chance to explain the why this. Yeah. Yeah. Since the rate calculator is largely invariant, right? So, for example, for peak 3, that is the magnetic field and the electrical point is the collinear. So the E square minus B square should be largely invariant. E dot B should be largely invariant. But if we dot B, for example, is not parallel and perpendicular, that means we can use Lorentz transform. You can transfer either E equal to 0 or B equal to 0. So if E equal to 0, then we don't have pair production. Okay, if B equal to 0, that means we cannot reduce the stream mass, so that we don't have enhancement. Yeah, so it's only when E and B parallel or anti-parallel that just gives the most efficient pair production. Yeah.
Maybe another question.
Yeah.
Inspired by previous talk, if you consider the Bringer rotating, is there any interesting?
Yeah, in total for an angle basically equivalent to a magnetic flux. Rotating is the other issue. Here we just give the simplest setup. Yeah, you could consider more complex configuration. Yeah.
Oh, other question?
Is there any way to understand the E over B factor by physical argument?
Physical argument, okay.
E over B.
E over B. Yeah, the only thing I can say like this, okay, let me actually I don't know, that's the okay, I think I can explain to you, yeah. Okay.
B over E.
B over E, yeah, B over E is larger, is larger, right?
Yeah.
Okay. Yeah, I just explained it here, you see. For this formula, we just pure magnetic field without the electric field. That's the equivalent B over E equal to infinity, right? So you see the polarization here. So for example, for the spin 0, 1, we just the mass is lifted. So B over E for the you have for example the factor here you have the factor B over E. Actually, if no E, that B over E equals to infinity, right? So this is since we have the minus sign here, so that's the rate should be vanishes. So that's the reason why if B over E is large, in this formula, in this guy, the scalar part and spinor part all gone. The only thing left is a vector contribution. Because for vector 1, you have this one. This should give the largest rate. If all the mass should be same, right? But for the other polarization, you use it for the same reason. Yeah.
Okay, let's say Jianxin, thank you.
Okay, thank you. I have an answer. Okay.
You discovered the pair production?
No.
That's too much.
Okay. I should say this. You know what I said? Don't believe, yeah. Even though I said the rate in principle you can do detection, but actually to rate is much harder. Because for example, I'll say one word, okay. We say our string on top of our D3 grid, right? If you want detection, the lab you put has to be directly under the D-spin, right? But the existence of D-spin just deal by a D3 grid should be very scanty. It's very, yeah. So the lab you can put any place, right? We have infinity logic. So the chance you just put on below the D1 spin, the chance is very small. Yeah, right. So actually the detection is not easy at all. Yeah. Okay, since we finished the first round of the workshop, yeah, we're going to begin the next round next year. Yeah, that's we are going to according to what we have before. Yeah, we should have it in China. That's what we have. So.
Yeah.
Yeah, so we have Xi'an, yeah. Yeah, so welcome. Yeah. Probably, I don't know, we have the fixed time because now we got a customer something like around the end of October or beginning of November, something like that. But I guess probably we're going to do a little bit earlier because once the winter comes, the heating, where you use heating, then the air may not be good. So we try to probably a little early. Okay, thank you.
So, kind of lesson for